We are going to examine the mechanics of supply chain operations through the lens of a single definitive metric, throughput. To understand system dynamics accurately, we have to separate the physical act of manufacturing a product from the financial event of generating revenue. Traditional manufacturing operates on a straightforward assumption. Producing a higher volume of items automatically equals higher operational efficiency. This creates a central tension in supply chain management. Maximizing production at every isolated station frequently increases overhead and inventory costs without actually increasing the money entering the business. The formal framework for diagnosing this, defined by APICS and the theory of constraints, relies on strict boundaries for what qualifies as throughput. This diagram outlines the exact formula. Throughput equals sales revenue minus truly variable costs. In almost all operational contexts, those variable costs represent direct raw materials. This formula measures the exact speed at which an operation converts raw value into recognized incoming revenue. Evaluating a system with this metric reveals its true operational performance. It forces management to shift its focus from lowering localized unit costs to maximizing system-wide profit generation. Unchecked production that outpaces actual sales creates an accumulation of operational cost and dormant inventory. It does not create throughput. Consider a physical example: a factory successfully processing and shipping 1,200 finished units to customers in a single day. Or a digital example: an e-commerce fulfillment network processing $2 million a week in shipped orders. Both examples share a strict qualifier. The output only counts as throughput if it reaches a customer and generates recognized revenue. We can observe how this metric behaves by examining the physical structure of a multi-step supply chain. For throughput to exist at all, 4 structural conditions must be met: demand, flow, a constraint, and delivery. This 3-node model illustrates these dynamics in action. The first step, machine A, possesses a production capacity of 20 pieces per hour. The final step, machine C, also processes 20 pieces per hour. The system anomaly sits in the middle. Machine B can only process 5 pieces per hour. Watch the flow of demand entering the system at machine A. The immediate physical consequence of this mismatch is a severe backlog forming directly in front of machine B. Pushing machine A to its maximum efficiency of 20 units per hour accomplishes nothing. It simply converts raw materials into trapped work-in-process inventory. The math is entirely unyielding. Regardless of how fast machine A and machine C operate, the total revenue-generating output of this system is capped at exactly 5 units per hour. System throughput is strictly limited by the capacity of its slowest node. Therefore, achieving high efficiency at any non-constraint is a statistical illusion. Those physical limits define the abstract characteristics of the throughput metric itself. Throughput is inherently time-based, system-wide, and revenue-focused. It cannot be measured accurately at the departmental level. Because total output cannot exceed the bottleneck's maximum speed, throughput is a constraint-driven metric. The prevailing management logic used to control these types of environments is known as the theory of constraints. This chart outlines the 5-step continuous improvement loop central to the theory of constraints. Phase 1 requires identifying the specific constraint that limits the system's overall flow. Phase 2 focuses on exploiting that constraint. This means extracting the absolute maximum output from the bottleneck without spending new capital. Phase 3 requires subordinating and synchronizing every other non-constraint machines to match the precise pace of the bottleneck. Subordination introduces a counterintuitive reality. Intentional idle time at non-bottleneck machines is both acceptable and necessary. Forcing a non-constraint to run at 100% utilization actively damages the supply chain by clogging the floor with unsellable inventory. Managing system flow successfully requires operators to protect the primary constraint above all else, which often means explicitly sacrificing local efficiencies. We can scale this logic up from the factory floor to macro-level supply chain planning. Sales and operations planning departments use throughput modeling to ensure incoming demand forecasts align directly with real-world supply constraints. In logistics, these principles govern the design of modern distribution centers, structuring facility layouts to eliminate physical bottlenecks during order fulfillment. Yet, a major operational challenge persists across the industry. Managers routinely mistake localized machine utilization for true system throughput. This happens because legacy enterprise resource planning systems are typically algorithmically optimized for cost reduction rather than continuous flow. These software systems instruct managers to overproduce non-bottleneck items simply to lower the calculated cost per unit, a practice that secretly drains cash reserves. Agile supply chains are currently abandoning those cost-centric algorithms, replacing them with flow-based metrics to build operational resilience. A supply chain optimized purely for cost will fracture under a sudden demand shift. A system optimized for continuous throughput can absorb those shocks and adapt. Let's review the shift in operational logic required to master throughput. First, high local efficiency does not automatically translate to high systemic throughput. Second, pushing a system to produce more physical inventory does not increase throughput if immediate demand is absent. The operational truth is absolute. Only shipped, sold, and recognized output counts. If you want to audit your own system, begin with this first question. What specific step limits your total system throughput? Second, is the output you are currently generating actually sold to a customer or merely being produced to sit in a warehouse? Third, are your continuous improvement efforts increasing overall system flow, or are they just boosting local efficiency? You must analyze your current operations to locate your true hidden constraint. Identify the specific daily activities that are increasing your operational costs without increasing your throughput. Mastering throughput and understanding the constraints that govern it is the definitive bridge from local optimization to global profitability.